In this video, I'm going to be talking about uniform circular motion, and I'm going to be deriving the equations for position, velocity, acceleration, and force. So uniform circular motion is when we have a body, like this, shown here, revolving around another body, circular motion, with constant speed. And know that constant speed does not mean constant velocity, because even though the speed is constant, the direction of the body is changing, so the velocity is changing. Now, I'm going to draw our position vector, P. So we have this position vector here, P, and the motion of the object is like this now. It's represented by this red circular kind of arrow. Redraw that. So this is how the object is moving. And if you notice, the magnitude of P is R, the radius of the circle, because that's the distance between the two bodies. So the magnitude is R. And we have this angle here, let's label it theta. And now if we split P into its components, like this, we have that the magnitude of this part here is R cosine theta, and this part here is R sine theta. So now we can start the actual calculations. We have that the position is equal to R cosine theta I hat, since it's a vector, plus R sine theta j hat. And with the velocity, now we can get velocity, because we know that velocity is the derivative of position with respect to time, which is dp by dt. This equals d by dt of R cosine theta I hat plus R sine theta j hat. And so we use chain rule here. Since R is a constant, we have R times negative sine theta I hat times d theta by dt plus R cosine theta j hat d theta by dt. And we're going to replace all the d theta by dt with omega, lowercase omega. That represents the change in angle with respect to change in time. So we get R omega negative sine theta I hat plus R omega cosine theta j hat. So now we can find our acceleration in the same way. We know that acceleration is the derivative of velocity, dv by dt, and this equals d over dt of R omega negative sine theta I hat plus R omega cosine theta j hat. This equals R omega, since omega is a constant, negative cosine theta I hat d theta by dt minus R omega sine theta j hat d theta by dt. So again, we just replace all our d theta by dt's with omega. So we get R omega squared negative cosine theta I hat minus R omega squared sine theta j hat. And we can factor this to get omega squared times negative omega squared equals negative omega squared R times cosine theta I hat plus sine theta j hat. Now, if you notice, this whole part here is our position. So you can see that this is just the position. This relates back there. So we can replace that, and we get equals negative omega squared position vector. So now we have the acceleration. Now we can, the force is just mass times acceleration. And acceleration is this. So we have the force is negative m omega squared p. We can simplify our formulas by, if we want to just deal with the magnitude, not the direction of these. So the magnitude of the position is just r. The magnitude of the velocity is r omega. Or we can rewrite this as omega equals the absolute value of velocity over r. And then the absolute value of acceleration is equal to omega squared times r. And we can replace omega squared with this. Squared r. And this will give us this. So the absolute value of velocity squared over r. So now we can simplify r. And so the absolute value of the force is now equal to m of the velocity squared over r. So these are just the scalar quantities.